Yay.
Okay, welcome to chemistry class. Yay! Okay, let's talk about percent composition real quick. Percent composition is when you take a formula for any compound and you calculate how much percent each of the parts is. So I'm going to do an example on the sideboard here in just a minute. Percent composition can be determined by calculating its chemical formula. You calculate the molar mass, and you take the mass of each of the atoms and divide it by the total. So I'm going to do sulfuric acid right here on the board. Hopefully everybody can see it okay. H2SO4, sulfuric acid. So we know in sulfuric acid, and you've already been doing this all week, there's 2 hydrogens, 1 sulfur, and 4 oxygens. Okay? So what we can do is we can calculate the molar mass, and we have to do that in order to do a percent composition. So 2 hydrogens times 1, 1 sulfur times 32, 4 oxygens times 16. This is 64. That's 32, and that's 2. I think we did this one for bell work yesterday or the day before. This is 98 grams per mole. Now, in order to calculate percent composition, all we need to do is take each of these pieces and divide by the total. Remember, the percent of something is simply a part divided by the whole. What's the percent of the boys in this classroom? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 divided by 27. 11 divided by 27, the part divided by the whole. So in this case, to calculate the percent hydrogen, we're going to take 2 divided by 98, and then in order to change it from a decimal to a percent, we multiply by 100. 32 divided by 98 times 100, and 64 divided by 98 times 100. Okay, once I calculate these 3 percentages, I'll get roughly 2%, roughly 33%, and roughly 65%. Now, when you get your final answers, I don't always recommend rounding them off to the whole place, okay? So you can leave some decimals there. The check on your answer is that all 3 of these need to add up to 100%, right? So check your answers. If you've done too much rounding off, they won't round off. They won't add up to 100%. So your percent composition has to be for each of the elements inside here. Okay, and I think you saw in last night's homework there's a couple problems like this, and I didn't realize we hadn't gone over that. Okay, so 2%, 33%, 65%. We would say high sulfuric acid is 2% hydrogen by mass, 33% sulfur by mass, and 65% oxygen by mass. And we can do that with any compound. And we already know how to do that because we already know how to calculate molar mass. It's just taking each of the parts and dividing by the whole. Very simple concept. You will see some problems, not only for homework, but on the test. Calculate the percent composition of nitric acid. Calculate the percent composition of water. Calculate the percent composition of whatever. I give you the formula. You should be able to do this. Okay? Questions? Okay. The bulk of the rest of this today's lesson is doing this backwards. Okay, and it's called calculating an empirical formula. We're going to take a percent composition and work backwards to figure out what the formula is. This is done in chemistry a lot, in forensics, in crime lab work, in medical labs, where they can take a machine called a mass spectrometer, which tells them they put something into it, it burns it up, it analyzes the masses of all the different elements in there, and it tells you you have something. You have found something at the crime scene or something in somebody's body that is 22% carbon and 18% oxygen and 5% sulfur or whatever. It gives you the percentages, but you don't know what the substance is. And then a chemist would take that and back calculate those percentages and figure out what the formula is for that substance, and then try and identify the substance based on its formula. Okay, so this is done every day in labs or all around the world. Before we do that, I want to talk about these 2 words, empirical formula and molecular formula. I left this up here from 6th period yesterday, okay? So the word empirical formula Empirical, write it down, is defined as the simplest, I've got a definition here, the smallest, it says here, or the simplest whole number ratio of elements. Now you can have different compounds that have different ratios. For instance, C2H4 is a compound called ethyne, E-T-H-Y-N-E, or sometimes the common name is acetylene, okay? And we could have C3H6 or C4H8. And I told you way back when we were in chapter 7 or 6 when we were naming ionic substances, and these aren't ionic, but when we were naming substances to always kind of simplify these numbers, right? But in organic chemistry and even sometimes in inorganic chemistry, we'll see things like this, where these are different substances. They have different properties, different boiling points, different melting points. Some of them might be a liquid, some of them might be a gas, but they all have the same empirical formula, which in this case would be what? What can I reduce all of these down to? CH2, right? Divide this by 2, divide this by 3, divide this by 4. All of these are going to be a 2-to-1 ratio of hydrogen to carbon. So the empirical formula for all three of these substances would be CH2. However, the molecular formula for each of these is different. And you're going to need to know those two words once we start using these problems and as well. So the empirical formula is the smallest whole number ratio. That's the first thing we're going to learn how to calculate. And then we're going to work backwards and figure out the molecular formula. Okay? For instance, the molecular formula of hydrogen peroxide is H2O2. That's the formula for that stuff you put on your cuts to remove all the germs and stuff from. The empirical formula would be HO. Now there is no such thing as HO. HO doesn't exist as a compound, but the empirical formula would be HO, the molecular formula for hydrogen peroxide, H2O2. Okay, so two different kinds of formulas, the simple one and the expanded version. Okay, molecular formula is the definition, specifies the total number of atoms of each element in a substance instead of the simplest or the smallest whole number ratio. Okay, so get those two definitions down, and then we're going to work a problem or two from section 4. Okay, let me get a fresh screen loaded up here. Cool. No. Okay, let's talk about this. I'm going to do a problem from the book again, so you can look back at it. You can see how the book solves the problem. You're going to see my method up here. These problems are very detailed in the steps. Please copy this down, every little detail, because when you do these for homework, you're going to want to say, okay, what did he do next? Okay, I need to do that next. What did he do next? He did that next. Okay? The problem is on page 343 if you want to follow along, or you can look it up later. And it says you are given only the chemical formula. No, that's not what I want to do. Sorry. I'm going to do the problem on 345. You are given the percent composition of methyl acetate, and must find the empirical formula. Before you can assume, because you can assume each percent by mass represents the mass of the element in a 100-gram sample, the percent sign can be replaced with the unit grams. Then convert from grams to moles and find the smallest whole number ratio of elements of moles of the elements. Okay, so here's what we're given. We're given carbon equals 48.64%. We're given hydrogen is 8.16%. And we're given oxygen is 43.20. Okay, so this is what we start with. question is, what is the formula that makes this up? What is the empirical formula that makes up this compound? We know it's carbon, hydrogen, and oxygen, but we don't know how many of each atom. So the first thing, and they've given you a clue in the instructions here, so this is a good one, you're going to change all of these. You're going to assume 100 grams. So if I had 100 grams of this methyl acetate, then it would be 48.64 grams of this, 8.16 grams of this, and 43.20 grams of this. Nothing's changed because we know that the percent times the total equals a number. So this percent times 100 equals 48.64. This percent times 100 equals 8.16. So I just change them all to grams. After you do a couple of these, you can probably just skip writing down percent and just write down grams. We're always going to assume a 100-gram sample. And that makes this easy. This makes it very easy because these add up to 100 grams. This adds up to 100%. Okay? The next step is we're going to change all three of these to moles. How many moles of carbon is this? How many moles of hydrogen is this? And how many moles of oxygen is this? Now you already have learned how to do that this week. So let's put our little conversion factor here. It's going to be molar mass, grams per mole, grams per mole, grams per mole. Carbon is 12, hydrogen is 1, oxygen is 16. Okay? Use your periodic table, you look them up, and then we're just going to grab the calculator, crunch these numbers. Okay, first one's going to be 48.6, 4 divided by 12, 4.053. I'm going to leave a couple extra decimals in the middle here for a reason, okay? So I'm not worried about sig figs right now. 8.16 divided by 1 is 8.16, good. And 43.2 divided by 16, 2.7. Okay, so now I have 3 moles. Now we know the formula of any compound. The subscripts show me the ratio of the atoms to each other. So here, in theory, I could write my formula now, but I'm not going to because it'd be wrong, okay? I could write C, 4.05, H, 8.16, O, 2.7. Now, you look at that and say, well, that looks really weird, Mr. Debski. You've never put decimals for subscripts before. No, and I can't, okay? But this would be true. The ratio on a molar basis of carbon, hydrogen, and oxygen is 4.05 to 8.16 to 2.7. Everybody understands that, right? But we can't write that. We have to find a whole number for all 3 of these that is still the same ratio for all of these. Okay, so somehow I need to take these 3 numbers and change them into whole numbers. Okay, so here's the next step. I'm going to look at these 3 numbers. I'm going to divide them by the smallest of those 3 numbers. Okay, so I got 2.7, 8.16, 4.05. 2.7 is the smallest one. I'm going to divide all 3 of them by 2.7. At the very least, that's going to change this to a 1. Okay, so I divide by 2.7. I divide by 2.7. I divide by 2.7. Now, what that's going to do for me is at least change one of these into a 1. It's going to change my oxygen into a 1. Now, hopefully, in most of these cases, at least in chemistry, chemistry here in high school, we should see something happen here that sort of makes sense. So 8.16 divided by 2.7. Wow, that's 3.02. I'm going to write it like that for a second. I'll explain in a second, okay? And 4.05 divided by 2.7 equals 1.5. Now, would everybody agree that 3.02 is really, really, really close to 3? Okay? So I'm going to say, for the purposes of this problem, that that's a 3. This is a 1.5, and that's a 1. Well, we're getting closer to whole numbers, right? This is the same ratio as this. As long as I divide or multiply a set of numbers all by the same number, they stay in the same proportion. So these are still in the same ratio as this, 4.05, 8.16, 2.7. And I'm a lot closer. I got 2 whole numbers. How can I get 3 whole numbers? Somebody raise a hand. Isaac. Multiply them all by 2. All 3 of them. If I multiply one of them by 2, I got to multiply all 3 of them by 2. So 1.5 times 2 equals
3.
Yeah, as soon as I see that 0.5, I'm looking good, okay? 3 times 2, 6. 1 times 2, 2. Okay, so here's my 3 numbers, 3, 6, and 2. They are all whole numbers now. And so now I can write my empirical formula, C3, H6, O2. Done.
Whenever you divide on that third step or whatever, you always want to use
The smallest one. Always use the smallest one. That will always, because if you don't use the smallest one, it's going to give you some fractions over here. Okay. So you always want the smallest one to be a 1. Everything else will be bigger than 1. And then you can try and find something to multiply by to get those to be whole numbers. If you see a 0.5 here, multiply by 2. If I saw a 0.33 or something close to a third there, multiply by 3. If I saw 0.67, which is 2/3, multiply by 3. If I saw something like 0.25, multiply by 4, right? So we're usually going to get 1 or 2 of these to be really close to whole numbers, and then the last one we're going to say, oh, how can I get that one by multiplying to get it to a whole number? Okay, and so this ratio, 3, 6, and 2, is super close to our original 4.05, 8.16, and 2.7, within the error of our measurements of molar masses and the way we rounded things off. Okay, any questions here? I'm going to do another one. Okay, this is a little bit of a longer problem. Does everybody understand? This takes some steps. This is not a 2-step problem. This is change them into grams, change them all to moles, divide by the smallest number, and then multiply if needed to get them to whole numbers. You might want to write that down. It's like a 4-step process, okay? Change your percent. Anybody want to write that down? Number 1, change percents to grams. Just change the units. Number 2, change each of the grams to moles. Number 3, divide by the smallest number of moles. Divide all of the elements by the smallest number of moles. And then step number 4, look for a multiplier that will give you all whole numbers. Okay, so that's a 4-step process. I've never really written it down before. If you do enough of these, you'll get the hang of it. Okay?
So is it always going to be 100 gram sample?
Yes. Because these are percentages. If they give you percentages, it's so easy just to say, hey, I got 100 grams. Now, if the problem gives you a number of grams of something, we'll probably do one like that maybe beginning next week, then you just need to eventually get it to moles. Okay? You can start with the number of grams, multiply by the percentages, and then change them to grams. It's just an extra step. Okay?
Can you say step 2 and 4 again, please?
Okay, step 1, change your percentages to grams. Just change the units. Number 2, change grams into moles using molar mass. Step number 3, divide by the smallest number of moles. And then step number 4, look at these numbers and find a multiplier. What we did here was we found a number, it was 2 in this case, that would change all of these to a whole number. Okay? Okay, let's do another one. I'm going to take one from the back of the book here, page 980 something or other. Find. Okay. Analysis of a compound indicates the percent composition of, and this is on page 982 if you like, number 26. Just in case I accidentally give it to you for homework sometime in the next couple days. Okay, nope, it's not 26, it's 27. Sorry. Okay, analysis of a compound determines I have 42.07% sodium. And I'm just going to write grams, okay? So I'm fast forwarding here. Again, it says percent, but I know Mr. Debski says the first step's always going to be change those to grams. So if you understand that concept, you can just write down grams. You can skip writing down percent and then changing it to grams because the numbers don't change. 42.07% sodium, 18.89% phosphorus, 39.04% oxygen. And again, so I wrote down grams. Don't be scared, okay? Remember percentages. We're going to assume a 100-gram sample. It's always going to be grams. This is just going to be a little bit more board space, okay? So, you can start working on it right now. You know how to change things into moles. Grams per mole. For oxygen, grams per mole. Phosphorus, grams per mole. Sodium, 23, 28, 31. Sorry. Yes. And oxygen is 16. Okay. Get your calculator out. 42 divided by 23, 18.89 divided by 31, and 39.04 divided by 16. No, 1.829. And again, in this middle steps here, leave a couple decimals. I'm not saying 10 decimals, but 2 or 3, sometimes 4 decimals. It's okay. We're going to lose them eventually. It's not a big deal. 18.89 divided by 31. This is the kind of problem where rounding off can hurt you. Round off to 0.609. And 39.04 divided by 16 is 2.44. Each of these is now in moles. So we have a mole ratio between these two things. Okay, what's the next step? Divide by the smallest one. So 0.609. Divided by 0.609. Divided by 0.609. Oh, I can see where this is going already. I like it. 1.829 divided by 0.609. 3.003. Guess what? I'm going to call it 3. Okay? 0.609 divided by 0.609, 1. 2.44 divided by 0.609. It looks like it's going to be close to 4. Let's see if it is. 4.006. Yeah. Okay. If you got something out in the thousands place, we're gonna drop those. We're gonna truncate. Okay. I'm done on this one. I don't need to do that last step on this one. My formula is Na subscript 3 P 1 O 4. Hey, what's the name of that? Somebody raise a hand. Sam? Oh, Melody? Yeah. Say it.
Sodium phosphate.
Yeah, sodium phosphate. We know him, right? -3 ion, 3 + 1 ions, sodium phosphate. Cool. Okay, so this one didn't need that last step. Questions? Okay, good. I like it. Okay. Now, there's one other type of problem which asks you to calculate the molecular formula. Now, the molecular formula will take one step more after you get to this answer. The molecular formula problem always has to give you one extra piece of information. Okay? Let me find one here and we'll do one more. We're doing great on time here. I did want to go over last night's homework, but if you don't, then I'll just collect it in a few minutes. Yeah, that too. Okay. I'm going to do number 30 on this same page. 982, number 30. You know what's cool? I like reading these problems because this one's about eucalyptus leaves. Who eats eucalyptus leaves? Huh?
Is that just
Yeah.
solid?
No.
Who eats eucalyptus leaves? Bailey?
Pandas and koalas.
Yeah, pandas and koala bears. That's their favorite food.
You were asking which one of us.
No, I said who. Not, oh, I meant, yeah. What animal? Okay. I'm not that kind of animal. So that's koala bears and panda bears. That's their favorite food is eucalyptus leaves. So eucalyptus leaves have all kinds of healing properties. Again, when biologists find a new plant in the Amazon jungle, they take it back to lab. They put it through one of these mass spectrometers. They figure out what's in it. They figure out if they can make an artificial version of what's in these plants, and then they do tests on animals and say, does it cure cancer? Does it solve blindness? Does it prevent malaria? All these cool things, okay? So eucalyptus leaves are the food source for panda bears. There it is. Eucalyptol is an oil found in these leaves. Analysis of eucalyptol indicates it has a molar mass of 154 grams per mole. Now, here's what I do. And again, please put this in your notebook. In the upper right-hand corner, I'm going to write down 154 grams per mole. What am I going to do with it? I'm going to save it till the end of this problem, because I don't need it till the end of this problem. But I want it on my piece of paper. Right? That's my molecular mass, or molecular weight. Okay, what's my percentage composition? 77.87 carbon. And I'm just going to write down grams because I know the first step is always to change the percentages into grams. 11.76 on the hydrogen. And 10.37 on the oxygen. Notice there are millions of compounds that have these three elements in them. Seriously, just in your body and around us on Earth. Millions and millions and millions of combinations of C, H, and O. Okay, so it says determine the molecular formula. We're going to start by doing exactly the same thing we just did. Change all of these into moles. Do you understand? Who's got carbon, hydrogen, oxygen masses memorized already? Carbon 12. Oxygen 16, hydrogen 1, right? So these ones should come 16 grams per mole, 1 gram per mole, and 12 grams per mole. Make sure your units cancel out. If you ever get stuck, because there's a lot of writing on your page here, make sure your grams are in the denominator. Get your old calculator out and divide these. 77.87 divided by 12. 6.489. Interesting. That's really close to 6.5, but right now I'm going to wait and see. Okay? 11.76 divided by 1. 11.786. And 10.37 divided by 16.
8
Where?
7.6.
You being picky. Thank you, George. And 0. What? No, I did something wrong. 10.37 divided by 16. Yeah, 0.648. Okay, so here's our three numbers. 0.648, 6.48, and 11.76. Now, let's do the steps we did. Divide by the smallest one, 0.648. Let's change the blue here, 648, 648, 648. Okay. 0.48 divided by 0.648 is 10. Everybody see that one? I like that, okay? Down here, this is 1. And the only one I don't know is that weird one in the middle, 11.76 divided by 0.648. 18.14. Okay, I'm going to stop and look at these numbers. Can I use these numbers, or am I worried about this? And guys, there's no rule. There's no rule in chemistry that says what to do and what not to do. This is a judgment call, okay? In a problem like this, your question is, do I need to multiply all three of these numbers by something to get rid of that 0.14, or can I ignore that 0.14? And I wish I could tell you the answer, but you're just going to have to learn by doing a lot of these problems and experience. In this case, I'm looking at a pretty big molecule already. We're looking at C10H18O. That's pretty big already. I'm going to look at the answer real quick here and see. Yeah. So since that's pretty big, I'm guessing we're not going to multiply. If I had to multiply this to get 1, what would I multiply by? Like 8 or something like that? 8 times 0.15 would be, yeah, about 100. No, 120. So it'd be 7.5. These numbers would be huge. I'd have 70 of these. This is getting out of control. If you see something that gets really out of control and you look at it, hundreds of atoms, it's not right, okay? We don't do that in high school chemistry, okay? So my ratio here, so in this case, we're going to say, these are big numbers already, C10H18O. Now that's not my final answer, that's my empirical formula. And the question was, what is my molecular formula? Now here's the last step. This is the molar mass of my molecular formula. What's the molar mass of this? Let's figure it out. 10 times 12. 18 times 1. And 16. That's 120, 18, and 16. 140, 154. Okay, so in this case, they are equal. Okay, so I compare this number, this is a bad example, I should have picked one where they're different. In this case, the molar mass of this is the same as the molecular weight. Now if they're the same, this is my final answer. The molecular formula and the empirical formula are the same. If this number happened to be 308, just for example, okay, they said the molecular weight is 308 grams, I would look at this and say, wow, that's twice as big as this. And then I would have to double all of my subscripts, okay? So your final answer, remember, the molecular formula is usually just a multiple of your empirical formula. It's going to be times 2 or times 3 or times 4 or times 5 or times 8. It's going to be some number bigger. So they're always going to give you this number if they ask you for the molecular formula. And your last step is compare the mass of your empirical formula to the mass of your molecular formula, and it'll be a whole number. You'll just need to multiply all of the subscripts by some number. Melody?
So for the final answer, like if that was 308 and you just have to multiply by 2, would the final
Oh.
answer be that formula?
No, it would be C10H36O2. If that was the molecular. Yeah, that's what I said.
Yeah.
Here. C20H36O2. If that was the molecular mass, yes. Okay? Chassis.
If it was like 3,
Oh my God.
how would you do that?
It won't. They will not. I will not give you one that comes out to be a fraction. It always has to be a whole number. If you had something like that, and you're looking at this, then you did something wrong. You go back and check all your work, because that means, oh, what? Okay? It has to be a whole number multiple. Okay? I won't give you those like that. Questions? Okay. I'm going to close this up for now. I'm going to pass out the rest of the bonus tickets. I'm going to figure out what your homework assignment is. I'm going to shut the camera off.
Bye-bye.
You have to slide this way.